Okay, this is going to be the first of two lectures on energy disaggregation, which is the process of, on a household level, trying to figure out what devices are being used at what times that contributes to this overall electricity demand signal that we are individually but also collectively sending to utilities. So this is going to be it's going to be one lecture as sort of a conceptual overview, and then we'll go into the details about non-intrusive load monitoring in the next lecture. And both of these lectures should be watched for Tuesday. We're going to put them both together because I've had to miss a couple classes, and that's put us behind. So let's start broadly and talk about electricity consumption by sector. In general, this is the landscape in the United States. More than a third residential, more than a third commercial, and about a quarter industrial. And transportation obviously is really small here. And so we know roughly how to divide up electricity consumption by sector, and we can actually provide more detailed information about each one of these sectors individually as well. So this gives you an idea of how electricity consumption in residential homes breaks down. And these numbers are in terms of kilowatt hours per year. And so this is obviously on average. There's quite a bit of variability by region and by household in terms of what devices are being used and what's contributing to electricity consumption overall. But this should tell you right off the bat that air conditioning is a really big source of electricity consumption in the United States. Then there's this other category, then lighting, water heating, refrigeration, television, space heating, and then down the line. So in general, we have an idea overall of, on an annual basis, where most electricity consumption, what activities represent most electricity consumption on the residential level. Now, the way we get that information, or those estimates, so those are estimates, right? We don't actually do any sort of energy auditing on a per household basis. And the process that EIA, the Energy Information Administration, uses to make those estimates is worth talking about somewhat. And so what they start out with is a giant training data set. So in general, what they're doing is they're taking a bunch of households for which they do have very detailed household level and even device level information about electricity consumption. And then they extrapolate that information out, throughout the greater United States, with a lot of, differences coming by region. And so, in general, electricity or energy consumption, we're not just talking about electricity here. Energy consumption is broken out into different categories of activities. There's space heating, air conditioning, water heating, etc. And the goal here is to try to figure out assign values to each of these individual activities. And we might have very detailed information about that for a fairly large data set of existing homes, but a data set that is pretty small if you're talking about its relative size to the total number of households in the United States. So it's a small sample, but a fairly substantial database. So once you have that database, and what that database really provides you is a record of tying certain types of behaviors, certain types of devices, certain types of homes to different patterns of electricity consumption, or not patterns, but total annual electricity consumption. And once you have that database, that training data set, then the goal is really to build a model from that data set that allows you to sort of like regression, model a household's electricity consumption on an annual basis as a function of information that you get on the household level from the homeowner about whether or not they use natural gas, whether or not they use a humidifier, how old their air conditioner is, stuff like that. So if we have this larger existing database of energy usage for certain homes and a record that we can tie directly to that information about the size of different people's houses and what devices they use, that gives us an ability to go out, send questionnaires and surveys to people whose houses we don't have any information about, and based on the information they give us, come up with an estimate about what the annual energy consumption for each individual house would be, just based on the answers from this questionnaire. And you can imagine that modeling. I had that equation up where it was total energy consumption. That green circle is a function of air conditioning, space heating, lighting, all sorts of stuff, water heating, etc. Modeling energy consumption for each one of those activities is its own exercise, right? Because there's a lot of variability about the types of devices that are used. You could have an old air conditioner, a new air conditioner. You could have a big house, which would require more energy consumption for air conditioning than a smaller house. You could have a house that is in the south, which would generally use more air conditioning or more energy for air conditioning than a house that's in a more temperate part of the country, at least that one that has more mild summers. So what we want to do is create models for energy consumption for each one of these individual activities, whether it's space heating, air conditioning, use of a water heater, based on information about climate. So we can quantify that in terms of cooling degree days and heating degree days. Remember, that is the relationship between the average, the daily average temperature and 65 degrees, where a cooling degree day is accrues anytime you have temperatures that are greater than 65 degrees. Heating degree days come about whenever you have temperatures that are less than 65 degrees. And so we basically want to come up with regression models for energy consumption for each of these individual activities as a function of more detailed information about home size, climate, etc. So not all variables in our regression here are going to be continuous. We might have discrete or integer variables, and that might, for example, indicate the number of different air conditioning units used, right? So you might have a really large house, and that term might be a function of climate, right? You might, in a really hot climate, you might have more than one air conditioner, but also house size. And then you make adjustments, and these are sort of like coefficients that allow you to sort of tweak, different values that go into this function that describe energy consumption from air conditioning based on more nuanced information like the type of air conditioner, the age of the air conditioner, etc. And so again, this all ends up forming some part of a regression where y is the dependent variable here. And that's what we're trying to predict or explain, and that is total energy consumption for a particular house, one particular house. And we might have a constant, or we might not have a constant. B's here are all the coefficients that we're trying to fit via ordinary least squares. And then x's are all the independent variables, and some of them might be linear functions or nonlinear functions. They might be, some of them might be binary variables or integer variables or continuous variables as well. And so for each one of these x's, it's its own separate activity. We'd have a separate model or regression model to predict x1 as a function of, heating degree day, average annual heating degree days, cooling degree days, the size of the house, etc. And same thing with x2, and same thing with x3, etc. And then all of these separate models end up being part of this larger regression that's trying to predict total household energy consumption on an annual basis. And this just explains the workflow here. It starts out with this training set of data. So we can't do any of this unless we actually do have a large database of real data, real energy consumption data on a household level, and along with that, real, accurate information about what devices are being used in those households and where they are in the country, and what type of climate they're in. And so we start out with this training data set, and then we are using that training data set to come up with models for energy consumption for each individual activity, based on the type of devices that are employed, etc., the size of the house, and then there's some effort here to start out with as much information as possible, and then gradually eliminate any sort of non-significant variables that go into the equation. The way you would do that is by running a regression model and trying to figure out which of the individual independent variables are statistically significant. In other words, which ones end up contributing substantially to the fitness of the model. And this is sort of an iterative process, but you end up with a regression model that is as accurate and as parsimonious as possible. And so then, in theory, you can model annual energy consumption for any household in the country as a function of what type of devices are used in that house, where it is within the United States, and typically EIA breaks the United States into a number of different zones. There's Western, Pacific, and Mountain zones. In the South, we have the South Atlantic, the East South Central, and the West South Central. Then there's the Midwest and the Northeast. And all of these are probably distinctive in terms of certainly climate, but there may be also consistent patterns across these regions and types of what devices are employed, and the sizes of houses as well. And so this is just for the sake of reporting. I think EIA makes an effort to compare individual households to their subregion, to their larger region, and then to the larger United States. And this is the end result of this process. So the EIA's goal here is to come up with an energy profile for average households in different states, different subregions, different regions, and then the United States. And keep in mind here, these are our estimates based off of these regression models. These are best fit estimates. Again, we're building these regression models using a training data set of information for existing households that allows us to model energy consumption as a function of a lot of different independent variables. And then we're using those models to take a guess about what the typical household energy consumption is, for example, in the state of Virginia. And how that compares in these pie charts. You can see a comparison between households in Virginia versus the average household in the South Atlantic versus the average household in the United States. And you can clearly see some differences here between Virginia and the United States. A main one is space heating in Virginia is lower than the national average, and that is because Virginia experiences generally mild winters, and air conditioning is higher than the average United States. And that's because people in Virginia use higher than average air conditioning because the summers are pretty hot. And there's some effort here to also break out energy versus electricity consumption into two separate categories. So this is all well and good, and it gives, I think it's a nice approach for trying to figure out on a household level, particularly on a regional level, and in terms of a lot of other defining characteristics of households like size, um, and the usage of individual appliances, what a particular household's energy consumption is going to be. And there's a lot of utility in that information from a system planning perspective, but also understanding how the adoption of different types of technologies alters energy consumption, as well as potentially how changes in weather and climate and demographic shifts can change consumption of energy, not just electricity, in different parts of the country. Now, what this doesn't give us any insight into is a dynamic, an understanding of the dynamics of energy consumption. So patterns of electricity consumption in particular on the household level. So how we change our consumption of electricity not only on a seasonal basis, but also on a daily and even hourly and minute-to-minute basis. And so a much different type of approach is needed to get at that information. So this is going to look pretty familiar, and we've talked a good bit about this, and you should be by now familiar with the visual of how electricity demand changes on not only a seasonal basis, but also on a sub-daily basis. This gives you an idea of how electricity consumption changes on a seasonal basis by sector. Now, overall, we've seen, I've showed you a lot of graphs about seasonal electricity demand dynamics, where in most parts of the U.S., or at least in the Southeast, electricity demand is highest in summer, and it's also high in the winter, and it's low in the spring and the fall. And a lot of that, of course, is due to heating and cooling demands, right? So periods of peak electricity consumption in the United States tend to be tied towards people's use of space heating and air conditioning. But you can see here that really the big driver of those dynamics is residential electricity consumption. Or energy consumption, or electricity consumption. This is electricity consumption. That's the most reactive sector to changes in weather here. And you can see that in terms of residential houses, in some cases, winter electricity consumption can rival that of summer electricity consumption. The dynamic aspect of residential electricity consumption is partially maintained when you're talking about the commercial sector. In particular, summer electricity demand is much higher than any other period of the year for commercial entities. But there's not as big of a peak in winter electricity demand for commercial entities. And then you can see industrial electricity consumption does still have some seasonal component, but it's really, really dampened. Industrial electricity consumption is, compared to residential and commercial, much more static throughout the year. So this is all something we know on a sector-to-sector basis. We're pretty familiar with how electricity consumption changes on a seasonal basis. But as we get to more resolved timescales, our ability to understand what's going on reaches some barriers. So we may even have a sense on a grid scale of how electricity consumption changes on a sub-daily basis, even on a sectoral basis, right? So we know what residential electricity demand looks like, commercial electricity demand looks like, and industrial electricity demand looks like on a sub-daily or hourly basis. And in this case, you can see the total demand profile in dark red, is a function of adding all of these other lines together, right? So you have agricultural and other electricity demand is pretty stacked throughout the day. Same thing with industrial. Commercial electricity demand peaks in the early afternoon, and of course declines basically in the late afternoon, especially after 5 p.m. Residential electricity demand, I'm not exactly sure uh, um, what uh, what region of the country this is for, but residential electricity demand here peaks at about 6 p.m. And this is definitely a summer electricity demand profile. And so when you add all this, the individual lines up together, you get this dark red line. So we have some ability to tell on an hourly basis how demand dynamics are changing. But here we're only identifying we're attributing different temporal patterns to different sectors, but we're still not on the individual business or household level, and that's where we want to get to. So again, we need special techniques to really get some insights on the household level, and that's really the end goal of having individual consumers make smart decisions about their electricity consumption, whether it's based on price or the availability of variable renewable energy. We have to get to that point, and so there are additional methods that are required to do that. So I think we've all heard a lot about smart meters or advanced metering, and there's sort of a difference. Advanced metering is this larger sort of umbrella term, and there are different types of meters that are in use in the United States. Um, but this is one way of understanding on the household level what individual homes are adding in terms of the signal they're sending to utilities in terms of electricity consumption. And there's two different types of metering. There's interval time of use meters, and these have been in use for years and years, right? And this gives you an hourly sense of how electricity demand is changing. So it might probably mostly reflect, if everything's aggregated to an hourly basis, it would reflect heating and cooling demands more than anything else. Now, smart meters or real-time sampling meters are two-way communication devices, right? So they're collecting information about electricity consumption at the household level on a minute-to-minute and second-to-second basis, and then they are sending that information back to central control systems operated by the utilities. Now, these are not the same thing as energy monitors like Nest technology, which are more sort of like fun gadgets that do have this potential to interface directly with consumers through your iPhone or the internet or something like that would allow you to either automate or directly control your energy consumption by remotely turning on or off or ramping down different devices in your home. That's different, right? Smart meters are collecting household energy information and sending it back to the utility, and so that's a much different technology than the Nest devices. Believe it or not, smart meters are really prevalent in the United States, and this was sort of shocking to me when I read this. But about 43% of households in the United States have two-way, smart meters where your electricity consumption data on the household level is obtained hourly and at 15-minute or sometimes less than that time resolutions and sent back to the utility. And they cost about $200 each, although this data is a little old. Maybe the cost is declining. And they require some sort of specialized technician to install it. So a utility will either contract with a company to install that or install it directly itself. And mostly the metered data is used for billing purposes, with a few additional benefits offered to residential customers. But the reality is we have not tapped the potential for taking advantage of a lot of the information that comes from smart meters. And part of the reason we haven't tapped that potential is because on the household level, the information that a utility gets is a little hard to interpret, right? It just tells the utility on a household level total electricity consumption for the house. So what they see is this blue line on the left, right? So power versus time. And ultimately, what would be really useful is for them to know, I mean, for a variety of reasons, which we'll talk about, what they would like to know is not only what the total electricity consumption is for each house, but where that, on a device level, where that electricity consumption is coming from. In other words, they want to disaggregate that power signal into usage profiles for different devices, whether it's your kitchen outlets, your microwave, electronics, your washer, your dryer, your air conditioner, etc. That's what would be really useful for them. So in recent years, there's been a growing interest in understanding how consumers use electricity and then being able to communicate that information in real time back to utilities. And so why? Who cares? So the ability to disaggregate real-time appliance level consumption data could have a lot of benefits. For consumers, it would give you an idea. I mean, a lot of times our devices are consuming electricity sort of without us knowing it. And so we could make explicit, deliberate decisions about how we program smart devices in order to, take advantage of lower electricity prices or, for other sort of grid-wide benefits. But it could also tremendously benefit electricity service providers and help come up with more targeted programs to employ energy efficiency and especially demand response. I mean, demand response is this idea that utilities in particular, would pay customers for a service of reducing electricity consumption during certain periods of the day in order to save money, basically. Or potentially to help integrate, renewable energy resources. And so having an understanding of what devices get turned on and off when would help implement some of those programs. And without customer level or at least household level information about energy use in particular on a device by device basis, we may quickly reach a ceiling for how effective a lot of these programs are going to be. So there are a lot of benefits for household device level energy disaggregation data. In other words, the process of going from this just single signal of electricity consumption on the household level on the meter outside your house that gets sent to the utilities into a more refined picture of what devices are being used when. Number one, that can empower consumers, right? If you have a better understanding of when you're using your devices and whether that's a deliberate decision or not, and how that overlaps with the cost of electricity potentially in systems where that changes for retail customers, that could make a big difference in terms of saving consumers money. It could also help with just automated commissioning and diagnosis of electrical components in either residential or small commercial buildings. It would again help come up with more targeted, accurate, or effective programs for either demand response or energy efficiency, but also help. In part of that third bullet is really having a better idea of validating some of the effectiveness of energy efficiency and demand response. And there's, the energy efficiency and weatherization is a business, and it's sort of sold to consumers as something that will save you money, except you have to realize that in a lot of cases there's an upfront investment involved in installing energy efficiency and weatherization measures in a household or a business, and it's hard to sort of prove that you're getting those benefits. And so on top of the fact that you're making an investment and there's a payback period, there's some uncertainty about whether that's actually working for you. And if there was an easy way to verify that and even provide consumers with an ability to maybe get their money back or have a discount or something like that, if it turns out that your energy consumption doesn't drop as significantly as the window salesman pitched it as, that could have a lot of benefits in terms of just making that industry more transparent and more accountable. And I think ultimately that would lead to greater adoption. And then, of course, if we're talking about the sixth, or is it the fifth fuel? I don't know. The energy efficiency sort of gets described as this. I can't remember if it's the fifth or the sixth fuel, or negawatts, right? So energy efficiency in some cases is the most cost-effective way for reducing carbon dioxide emissions or carbon emissions from the electric power sector. And that's not always the case, and that's only the case up to a certain point. But it is commonly regarded as the sort of unsung option, the least sexy option for reducing carbon emissions. And you can only take it so far, obviously, but and a lot of the benefits, we could derive a lot of benefits in terms of energy savings by increased information only, right? It would help consumers make better decisions and utilities make better decisions. And so this figure is basically plotting annual energy savings as a function of feedback type, where the feedback type is sort of how resolved the electricity consumption data is that utilities are getting from individual customers, right? So if you have enhanced billing, you can save 4% on annual energy consumption, and that just means maybe sending information to individual consumers that includes tips about how to save electricity or save energy during the winter or the summer. It could be like keeping your blinds drawn in the summertime until the sun's not shining through your windows and stuff like that, right? And I think we're all, if you pay your own electricity bill, you're pretty aware of the fact that Duke Energy is highly engaged in a lot of that stuff. And they might, I can't remember if Duke does web-based audits, but certainly there's an interest on the part of utilities up to a certain point in providing more information to consumers about how to save electricity. And then getting feedback directly from consumers in terms of their electricity consumption does end up paying some dividends on a daily and a real-time level. And the real-time plus appliance feedback, so that would be not only having information about on a household basis what electricity consumption looks like, but on an appliance device level basis, the benefits jump up to about 12% energy savings. So that's, I think that's the near-term target. But in theory, people have estimated that we could potentially achieve greater than 20% energy savings if we had fully integrated, smart meter data. In other words, every household and commercial building was equipped with a smart meter, and that information was disaggregated down to the device level. In theory, there's a way to translate that enhanced information into energy savings by just changing, pricing, dynamics, and in order to shift consumer behavior and stuff like that. And so that's sort of that's the target here. That's the end goal, is to really integrate this stuff in order to get energy savings. And that has, nothing to do with these other benefits that we talked about in terms of facilitating demand response and the benefits that could come along with that in terms of helping to integrate variable renewable energy. So in other words, having load shifting sort of play this sort of virtual energy storage mechanism. So that's not even included here. This is just in terms of energy savings. So the upshot here is that the potential benefits from achieving cost-effective, and that's an important idea here, cost-effective energy disaggregation on the device and household level are pretty significant. So at this point, I think, I've tried to sort of convince you that there's a lot of information out there about, how households and different sectors, including commercial and industrial, use electricity, how that varies throughout the day, how that varies throughout the year. And there's this next step that we have to take in terms of disaggregating that information down onto a device-by-device level. And so the question is, how do we get there? So the current practice is to submeter. And what that means is you install separate individual plugs on each power meter on each major appliance in the residence. And the problem, this works, right? We know it works. The problem is that it costs too much money. Because a smart plug, unless the cost goes down, is going to be prohibitively expensive. Not individually, but if you need to put a smart plug, which costs about $50, on every device in your home, and a lot of devices have between 5 and 10 major appliances, then you're talking about the submetering cost up to $500. And then if you're trying to get sort of a ubiquitous information flow, right, or at least adoption of smart metering and device level metering data, that's too much money. We can't expect everybody or every utility in the United States to pay for everybody to get this type of device level measurement installed at their houses. So we need some other way, some other non-traditional way to get sub-meter data for residential and commercial buildings. And this table just gives you an overview of the options for doing that at the moment. So there's smart appliances, plug level hardware, there's house level current sensors, and then smart meters. And the problem is a lot of smart meter data. Again, it says there's basically no cost to the consumers because the utilities are installing it anyway. The installation effort is really easy, and the adoption is really prevalent. The problem is smart meters don't give you that refined device level data. So if there was some way to come up with some sort of modeling or algorithm approach to using the smart data to sort of infer what types of devices are being used when, that would be perfect, right? Because smart meters are applied or have been adopted by basically 50% of all homes in the United States. And so if there was some way to use that information to get device level data without having to individually meter each big appliance, that would be the most cost-effective way to go about it. And so again, this is just reiterating that we really want to get this device level meter data, but at low cost. And what that effectively means is we want to use existing smart meter data or smart meters that are coming from residential and commercial buildings at the moment. Okay, so all of this has served as an introduction to what's called non-intrusive load monitoring. So this is an alternative way to get from the signal on the left, which is the output from a traditional smart meter, which is sending two-way. It's a two-way information device. It's collecting information in terms of your hourly or sub-hourly electricity consumption and sending that back to the utility, but it doesn't have any way of getting down to the device level data. But their non-intrusive load monitoring is a way to get from this blue signal on the left to an idea, or at least a really an estimate of what the true disaggregated power consumption is on the right, on a device level. So this is an analytics approach in order to disaggregate building loads. And so there are a number of algorithms that are used in order to do this. And this is a very competitive market at this point. This is an example of a sector in which software development and the cleverness and accuracy of individual algorithms is sort of shaping the industry. And so in a lot of cases, those algorithms can be somewhat proprietary. It's sort of like Google's search algorithm, right? You know sort of generally how it works, but the particulars of how it works and how effective it is something that directly determines the effectiveness, and so that's something to keep secret, right? It's like the Pepsi recipe or something. And so this is these algorithms, non-intrusive appliance or load monitoring algorithms. A lot of different people are working on them, and they have tremendous potential to provide this alternative solution to higher priced traditional submetering, right? So that this is a way around putting individual plugs on every single appliance in somebody's house in order to get an understanding of when they're using device level information about energy consumption. So here's some references. The next lecture is going to be on non-intrusive load monitoring. So I'm going to just load that one up and do it right now. Okay.